and there is some code for doing partial application. So this means, so if you give it a function, and all Haste functions are not applied directly, but use this a function kind of, if you give it an undersaturated list of so if the function, you give less parameters than the function expects, it returns your closure that is still a function, and if you give it more, if you give it exact number of parameters, it will just apply the function, give you the result. If you give more parameters, it will expect that the evaluation of the first parameters yields a function which then is applied to the remaining parameters. So this is really how Haskell function application works. And
so how did you run this example that you just did? Sorry, when you
sorry, how I ran it. This was here. I put it here. So the JavaScript file that Haste.
How did you actually run it?
Oh, I just load this HTML file. So if I click on this.
Right. Okay.
Sorry, this example thing is just a link.
Go ahead.
See here. It just loads this link.
Carry on, sir. Carry on.
Okay, so these are the most important parts of the runtime. It's really just less than 100 lines of JavaScript code to implement this. So other stuff that you find in the runtime, of course, they have to simulate low-level arithmetic. Same map it to JavaScript arithmetic. You find native JavaScript strings. You find stuff like for debugging purposes. Well, set timeout, of course, it's an important function JavaScript to kind of yield and have asynchronous computations. Well, you find a lot of stuff for DOM manipulations that we are completely not interested in. And some stuff for arrays and simulating pointers. So you can, by the way, with Haste compiles a good part of the of packages on Hackage. Well, template Haskell won't work, but you can still compile many packages by just kind of going to the code, patching out the template Haskell stuff, and Haste compiles it. The problem is, well, the packages that you compile might not run. So you might get runtime errors. But they try to implement all primobs in GHC and don't care so much about what they actually do. But often that's enough. You have, for example, you want to have semi-groups. Of course, you buy into unordered containers and hashable, because in this semi-group package on Hackage, there are instances for containers, and you still want to use a semi-group. You don't care about these instances. You can compile it with Haste and use it, as long as you don't happen to use these instances which compile but might give you weird behavior. I haven't tried if byte strings are usable at all in Haste. They might be, because they simulate pointers on, I think, on array buffers. But probably, even if it works, probably it's not really the right thing to do in order to get byte strings in JavaScript. Okay, so those are the things you find when you look in this runtime code. And this is the code that actually is a program. So if you compile this program, this is the JavaScript code you get. And starting from the bottom, this is just something that Haste generates. There are different ways you can tell Haste how you want to start your program or integrate it. Well, this is the default. It just runs it after loading the page. Here's the main function, and you see here's this application. So it has some function that is applied to some kind of argument. It's essentially just an encoding of an empty parameter list. And then you see this function _for is defined here. It just calls another function without an argument, which is this to function, which internally calls JS alert, which is a wraparound alert. Well, it does something to the string that we gave here as a string, somehow marshals it, and well, it assumes that the string potentially is a thunk, so it evaluates it first, but well, in this case, it's actually, so this evaluation is no, and well, that's it. And every Haste program has essentially the structure, just that you find a couple more lines here. And okay, so when you work with Haste, next thing you need to know about marshalling. So because often you want to link against do forum function calls against JavaScript function, or also sometimes things just fail, and you need to know how Haste represents Haskell types in JavaScript. And this is how it does it. It just uses an array, well, it throws away all type information essentially, has an array, and the first field of the array is just the number of the parameter of the constructor, and the other fields are the arguments to the constructor. So here examples, if you, well, these are boxed, of course, type representation. So certain situations it uses unboxed, for example, for booleans. Then it just uses a plain JavaScript value. But boxed int, for example, the 5 here is essentially there's only one constructor, so 0, and this is the value 5. For nothing, for example, there are 2 constructors. Nothing is the first constructor, so it gets the index 0, and this is an encoding of unit, I think. Yeah, I think. For just, we just take the first constructor, pass the argument, and well, here's an example for list. It gets a bit more tricky. Well, this, by the way, is an evaluated list. So it's usually you would have the list in a thunk. It's a lazy data structure, but this is when it's fully forced. You will get this structure. So you have there are 2 constructors to lists. In the end, we have here the nil constructor. You see it here at the end of the list. And well, in the beginning, we start with the const constructor. That's the 1. Then the first argument to the constructor is actually the value 1 here. The second argument, or this bracket, is the remaining list, the tail, which again is a const. It has as first parameter the value 2, and well, and then as second parameter the empty list. So this is how it works, and when you know this, essentially you can represent all Haskell data structures in JavaScript, and this can be very helpful when you want to get certain efficient, or you want to make your code efficient, or you have to write FFI functions. So how does it? Oh well, here's an example. This is just copy and pasted from the Haste runtime, but it shows essentially how it works. This is part of JSON encoding, but it's essentially taking an array, a JavaScript array, and produces an Haskell list, and so essentially, here the interesting point here is essentially here's where the list is constructed. You see, you have the, well, if the list is empty, of course, we return just the empty constructor as a nil constructor. Here we have a const constructor, and here you see that it's actually constructing a thunk. So it does not construct the structure that I showed you before, but it constructs a thunk that would generate the structure that I showed you before. So it just recurses, and if you would evaluate it using the e function, and you do it often enough, you do a deep stack essentially, then you would get the representation that I showed you before. And and then the other way around here, you see we turn back, this 2HS is for the JSON encoding, but so for the elements actually. So the other way around here, you turn a list into an array. There you see that it actually, in order to, you iterate over the array and extract the element, the array extracts the elements, over the list extracts the elements, puts them in an array, but you have to call the e function. If you forget it, and yeah, I found myself that I fixed lots of problems in our code by just injecting e, which is essentially, you know, when you're in Haskell, you put the bank pattern. And yeah, on the JavaScript side, you stick an e somewhere in. Yeah, if you get an undefined somewhere in an exception thrown in the Haste code, try an e, and it might solve your problem. Yeah. Well, or carefully design your code. Okay, how does foreign function bindings work? There are 2 types of foreign function bindings in Haste. The first is a static way of doing things, which is an older thing and more efficient, but less type safe. It just works like standard GHC foreign function binding. So you declare foreign import. This is the name of a JavaScript function. This is the Haskell symbol, essentially. And this is a type, and the type is allowed to only use primitive JavaScript types, essentially. So this JS string is fine, But if you want to pass an Haskell type, you have to wrap it into a pointer. So that. Okay, and then the dynamic version is, here's an example. So it's the same function, but essentially has this FFI function that evaluates the JavaScript code at runtime. Internally, it's an eval that goes on there. And here's examples how to use them. So it's, again, a Hello World program that implements alert kind of, or imports alert through foreign function bindings. Here's the first version. Here we use the second version. And here's a third version that I just show how to do callbacks. And here, essentially, this JS func, we have a Haskell function that we give to the timeout. So we call the alert only after, 2 seconds, I think? Yeah, 2 seconds. And here we import, essentially, the set timeout as function timeout. And we give it, it takes the Haskell function, takes an integer. And this is how we turn a Haskell function into these JS function types that we can pass to JavaScript. And so this part here is a Haskell function that we want to execute. This thing turns the whole thing into this type, then JavaScript callback, and here we apply it. So, yeah.
That third keyword, ccall, why do you use that? Because isn't that the calling convention of the language? So
I don't know. It's Haste really is, as I said, I don't know so much about Haste, but it's really just GHC kind of hack to have a different code generator. And Haste int, which is kind of the Cabal replacement, really is just a small Haskell program that calls actually the Cabal binary. They do not even link against the Cabal library. They call really the binary. So a lot of stuff is really just plain hackage, GHC kind of hacked around. And well, I guess that's the reason why they didn't change this. Yeah. Actually, in practice, there is a preprocessor that avoids a lot of boilerplate. For example, here you have to really put a single a plain JavaScript function. So often in JavaScript you have objects and you would like to put an expression there, similar like here, and then you have to write some boilerplate on the JavaScript side. In the package that I uploaded to JIT, there I write this boilerplate manually. In practice we use a preprocessor for doing it, and Haste comes as a preprocessor for doing this job. So you can essentially, you have a different primitive here, and then you can pass arbitrary JavaScript expressions, and it will generate the boilerplate. Okay, so we can run this again. Well, let's compile it. So compiling is the same thing, and let's run it, and we see that it behaves as expected. Here's a set timeout, so it waits. Well, it waits too long, so something went wrong. Have a look. Oh, it might be that on GitHub there's a wrong version of this thing. Let's see. Yeah, okay, sorry, I will fix it later. I think I fixed this, but it's not yet in there. Let me see where the problem is. No,
The version at GitHub is correct. I mean, it works for me.
I think the version that I have here is wrong. You see, it's a different code. Seems like something went through. The version of GitHub has the 3 functions in there.
Yeah.
I'm usually a Mercurial user, so Git always messes everything up. No, it's the, well, it works, but it has not the third call in there.
Oh,
yeah. I will fix it later. So yeah, sorry for that. Okay, yeah, I will upload this version later. somehow I reverted it. Okay, so so far to the first part. So this is kind of really basic usage of Haste. And now, well, what you get now is you can really write arbitrary Haskell code. So this thing compiles. You can use promoted types. You can use, well, actually in our code for our cryptographic code, we use lots of new types, type classes, type level numerals. All the stuff just works because Haste just uses GHC. So you can really use every language extension that GHC, well, except for template Haskell, but everything else just works. So the only thing is, yeah, if you happen to depend on it, you can compile a good part of Hackage. The only thing, if it happens to do some primos that Haste cannot really simulate, or it's using native bindings in C, well, the code might not run, and you get runtime errors. But yeah. So by the way, was anyone able to already compile Haste, install it? Probably not, but
yeah.
Oh, cool, it worked. Great. Okay, so that's the second part, and this is a bit more specific about how we use Haste. And I start with an example, and then I explain a bit like how we, well, our main